Welcome to week 9 of NPTEL-SWAYAM RL reinforcement learning course. Today, today basically we'll be seeing deep Q networks, policy gradient, and actor determinants. So first I'll introduce deep networks. So first let me start with what a neural network does. So neural network it basically acts as a function approximator. For Q star. So I give X my state and actions. I have a neural network where I might use a different notation from sir's lectures. So yeah, really sorry for that. So it gives you a function of my states and actions. So this I want to approximate theta square. So what I basically do is I have theta new is equal to theta old plus some function which depends on how you've arranged your deep network layers. So this function, how do you train this function is you get S, A, R, S trajectories. All the trajectories you get, you run it on a network, you give this as all the trajectories as an input, initialize theta. Theta is not the, this theta is not the theta with which you parameterize policy theta. Those two thetas are different. This is just a theta which the neural network does in this. Okay, maybe I'll change this to some. A, neural net parameter A. So how to pick these we have seen in multiple classes. Now you can pick it online, you can pick it offline, you can pick it on policy, you can pick it off policy, you can pick it like anyway you want. So yeah, but what happens here is, suppose you pick S0, A0 and you get R0. Right, and S1. Depending on the action, you have S0, you pick an action A1, you get a reward R0, you go to S1. Once you go to S1, depending on your initial policy that you have, you pick an S1, you pick an A1, you pick an R1, you go to S2. So there is a correlation built up in this kind of scenario where so once you pick an action, you will only see those states. So this is basically a type of after states. You will basically see those states which are correlated with the action that you have taken or with the policy which you have initially chosen. So generating these trajectories, you will not be able to go through all the states action pairs in the trajectory. So for this, initially what happens is, given a policy, there could be stationary distribution. So in the last tutorial, you guys understand what a stationary distribution for an MTP is, right?
That's right.
In the last tutorial, you guys understand what stationary distribution for an MDP.
Yes, yes, yes.
So getting a policy, when you're picking for, given a policy, it could so happen that your station, it could go to a station distribution, like you start at some state, you are in some classes of the state only, the probability of going to other states is very less. So you don't sample from a whole subset of sets too often, because the MDP is designed in such a way that stationary distribution, the number of times you visit that state is very less. So this is a problem. So given a policy, there could be a stationary distribution on the SND pair. So last time we discussed it only on the states pair, states, because that was a Markov chain. You can extend it to two-dimensional state action pair. State action pair, MDP, you could form it as a Markov chain. So
I think maybe you're confusing stationary distribution with deterministic probabilities, because
no,
the probabilities don't change. Not as in you go from one state to another, and
no, the probability of going from one state to another doesn't change.
yeah, right, right.
Okay. Yeah.
But I think you said you don't go to other states, but that depends on the probability.
No. No. Last time I said stationary distribution.
Yeah, stationary distribution. You said that it doesn't. You sample from the same distribution, and you don't change states. That's what you said.
Yeah, you're right. So but initially it changes. So suppose you initially you sample some Markov chain with two states, very easy, let's say 0.7, 0.3. If I have a Markov chain, like a proper Markov chain with transition probabilities, with transition probability matrix P. So E11, E12, E21, E22. Now, if my initial initial distribution is 0.7, 0.3. So what this means is, if I do, so if I start my experiment, if I start taking sample from, so this is basically I'm sampling from an MD, right? So when I start at state 1 with probability 0.7, I started state 2 with probability 0.3. These transition matrix don't change. This is time variant, time invariant. Time variant MDP, time invariant MDP. Time variant MDP is the transition probabilities have a they're a function of t. Okay.
Yeah.
Suppose I have a Markov chain which is state 1 and state 2, and it goes 1, and 0, 0. So now at time 1, the probability of it be, so what is the probability of you sampling 2 at t equal to 1?
Yeah, right. It swaps, right?
Yeah, it swaps. It's 0.7. So now you have the, so what you basically get is the probability that you will hit 2 varies. So this Markov chain has no stationary distribution. So
yeah.
For that better way, suppose I think 0.5 and 0.5 would give you a stationary distribution. So even if you start at 0.7, 0.3, you will end at 0.5, 0.3. So you can sample both. I think this also has no stationary distribution. Because if you start at 0.7, 0.3, I think you'll continue staying at 0.7, 0.3 or something like that. But
yes, yeah. But if you start at 0.5, 0.5, you will stay at the
0.5. Yeah. So the stationary distribution is like these things need to be properly designed. I don't have that now designed. I think I did in the last class where you start from anything, you will reach one distribution. You'll reach one distribution and you'll stay there. Now once you have stayed at a distribution, so what happens is initially the the probability of going to state 2 could be very high. But the stationary distribution, so initially at time equal to t, it could be like something like 0.7, but it could so decrease, and it could go to like 0.01 or something. The stationary distribution for state 2 could be 0.01, could stay more times in state 1 only. And for the state 1, it would be like it would start at 0.3 and then go up above, because they both should sum up to 1. This is for state 2 and this is for state 1. So now if you sample, if you have this kind of so something which gives you this kind of distribution, and if you sample it with starting probability 0.7 and 0.3, what will happen is, as you go to infinity, you will sample the state 1 more number of times than state 2. Does that make sense?
Yes, it does.
So this is the problem. Like now I have 2 states. So imagine you have multiple states, and given a policy, you could run into a stationary distribution which has very high probability of being in one subset of those states and not visiting other states.
No, it's not confusing. Because if it so happens that we converge to a high probability of staying in one state, then it's fine. But generally speaking, steady state distribution need not necessarily converge to very high probabilities. It could be uniformly distributed as well.
Yes, it could be. You're right. But yeah, you're right. But we are generalizing the case. So like you could run into problems where you have. So basically what I'm saying is, if you have an MDP which has station distribution such that, so given a policy of a station distribution such that some substates of those states run into, like you just sample those substates, you don't sample other substates.
Right.
Two chains and MDPs also is that your MDP becomes a Markov chain when you have fixed your policy. Unless you fix your policy, your MDP does not become a Markov chain, because MDP is a 6 tuple thing. So state, action, and all. So but once you fix your policy, like okay, you know your policy that if I'm in state 2, I'm going to take the action left, and you know when you take the action left, you're going to state 1. If you're in state 1, you fix your policy that you're going to take action left. If you're in state 1, you again go to 1. So once you fix a policy, then you can break down your MDP to a Markov chain.
Right. Yes.
So now MDP doesn't directly come to a Markov chain. You need a policy. So it's not just that MDP has station distribution, but you could choose a policy randomly. You could choose that, okay, I want to start with some policy where I want to sample it. That policy could give you a very bad station distribution.
Okay.
They use something known as experience. Okay, okay. You have watched the lectures of Sir, right?
Somewhat, not entirely.
So I think Sir did 2 experience replace kind of thing. One is I'm also not sure. One is replay buffers and one is I think transition buffers. I'm not sure, but I'll do replay buffers. Both are, so both concepts are basically the same concept, but when you what do you say? So it's basically experience replay. What you do is you have memory, you store all the trajectories. Anytime you go, you store the trajectories. Now, when you want to update, you don't update your this thing on what action you have chosen. You update on the memory. From the memory, you take some batch of trajectories, uniformly random, or with some distribution. It's not uniformly random. With some distribution, and then you update your details.
So with some probability, I'll choose to update from the experience of replay buffer.
Yeah.
With some probability, I'll choose to update from the action.
No. You'll always choose from replay buffer.
Okay. Okay.
So you'll run. So how it goes is you sample your trajectories, right? You sample your trajectories. You get these pairs, SA zeros, these pairs, right?
Yeah.
You store those pairs.
Yeah.
Even with low probability, maybe you have visited S1 some state multiple number of times. Those also will be stored. You have visited some small states less number of those also will be stored. Now you don't need to wait for the MDP to arrive at that state because you have a memory, because you're uniformly picking from those. You'll always have a good amount of probability that you'll pick from a state which has very low stationary distribution. Because if you have at least reached that state once, it will be there in the experiment.
Okay. Okay.
And the thing is that replay buffer will have same state action pairs multiple number of times. So if uniform, then those will get more distributed. But yeah, so it's
Right.
not
But
just uniform distribution. There are other distributions also could sample from, so that you give weight to you give some amount of weights to, okay, how much time it has been, like how much time it has not been, but let's not go into that. But replay buffer is basically it's a memory.
if I randomly sample from replay buffers,
Yeah, yeah.
uh, doesn't it actually? It kind of seems bad because uh, I don't give credit to the action that I took at previous say end states.
No, your action you'll choose from the policy that you have.
Yes.
So what you'll do is first you have multiple transition samples there. Okay, action you will choose from what policy you have, but yeah, the so so what it does is sample a transition. You sample the transition from the buffer
Yeah.
given an SA pair. Okay. So first we have which stores fast transitions. So yeah, so S T minus one, A T minus one, or S T. This goes into your buffer. Sample one transition from this buffer. Sample one transition from this buffer. Yeah. Now update. Okay, I used K old to K new. Now you have ST. You have ST. This is your current state. You choose your AT action with the policy that you are working on. Then you'll get a ST, AT, RT plus 1, ST plus 1. Push it into this buffer. Now select some sample uniformly from that buffer. Update your parameters for functional approximation of Q star. Now your current state is ST plus 1. From your policy, do your transition. Push it into buffer. Sample. Randomly, it could be any other trajectory. Update your Q, the Q function parameter update, random sample. Now does this make sense?
Yeah.
So policy actions are there. They are completely being stored in the buffer.
Yes.
So you are giving weightage to your action, what you're trying to take, and what policy also. Policy is being updated. That policy is being updated, but just that instead of just what updating on just what you have done now, you also sample. You you randomly sample from that and then you update, so that it's even the sample that you have done now might come up somewhere time later, but you'll update it with this
Right,
sample also.
right. Also, since the replay buffer is kind of like a FIFO queue, it will anyway get
Yeah,
sampled.
yeah, yeah. Okay, I hope this is clear. Then this, okay, then there is what I think there is a thing called trajectory buffer where you save all the trajectories and the sample of trajectories. But I don't think sir has gone into that. I think sir has just got replay buffer. Okay, so yeah. Yes. So this. Okay, so yeah. Next I'll go to policy. You have any more doubts in deep queue networks? So basically, all this, okay, this replay buffer is just a tool to do DQN. So the basic idea of DQN is to do a function approximation. Okay, so first there's a state approximation and then a function. So there are the whole network model where you have layers where you try to, your basic goal is to approximate your Q function so that you can max over. How you approximate that is, yeah, you have some parameterize the networks, basically find weights. They find the weights of this thing using stochastic gradient approximation and all those. But the stochastic, it depends on what input you give. So now that parameter here I have assumed to be k. So it updates k after by taking some inputs and then updating those weights so that you are more close to the q value. That is like the basic concept of this. Instead of doing it stepwise, for one step each, you have an experience relay buffer. So experience relay is this type of extension to deep QN, where instead of doing trajectory translations based on your policy and updating it on that thing, you have a replay buffer where you store all your transitions. You update it based on the transitions. Once updated, you have the new state, pick your action according to the policy. You'll go to a new state, that put it in the transition buffer. Then pick from transition buffer, update, put in transition buffer. I hope that is clear.
Yeah.
So policy gradient. Okay, I think sir has not been this much mathematical in this, but okay. So I'll write down some equations. I might be switching. I might be writing some notations like value function. I think value function. Okay, I'll see as I go on. If you have any doubts, stop in the middle. Okay, stop in the middle. Notational doubts basically. So. Okay, so let me define something known as capital pi. Okay, so capital pi is set of all parameterized policies such that beta belongs to parameterized policies. Does this make sense? You understand this one?
Yeah.
So this is set of policies that I have that I can represent with theta. Theta being my parameter with which I try to parameterize my policy. Now that theta also belongs to some set capital theta. Okay. So why this is necessary is because when you do policy gradient, what you are basically doing is you are updating your thetas, right? So now you have an expression for. Okay, so let me give the policy gradient. It's has done. So basically I'll write pi of s comma a theta. This is basically your function. So first the algo goes is you initialize theta 0. Something which belongs to this theta, so that you can parameterize. Okay. So next what happens is at each iteration beta k plus 1 is equal to beta k plus alpha k into grad some parameter performance measure of this things. I will go into this later. But do you see a problem with this expression?
It seems like green was a bit.
Yeah, you are exactly right. This seems like it was a pair. So why I'm being so specific is there could be some cases such that where your theta k plus 1 does not belongs to this theta set. So you could update the theta, the new theta. There could be no valid policy for the theta that you are updating.
Right.
So what you need to do is, so it's just a theoretical thing. So you just project it over. But basically your all discrete games and all doesn't run into this problem. The moment you go into continuous subspaces, this thing happens. Policy becoming, because you are using in continuous subspaces, you need to make sure that you do projection. So this is just for continuous. If you feel like I'm confusing you can stick to this definition. But does the projection make sense?
What does the project operation do?
Okay, so what does the project operation do? So suppose now, so
All right.
this is your theta. Suppose theta is the parameters. I'm using 3 parameters to define theta 1, theta 2, theta 3. Okay, so theta is a subset of R. Some plane which lies in R.
Okay.
Okay. Yeah. So I don't know how it's looking, but okay. So yeah. So now suppose I start with my theta 0, but it's a subset of R. It's not the whole of R. Okay. So I start with something on this plane. I start with something on a point on this plane. Now, while doing my updation, it would so happen that I go out of the plane and I land somewhere here. Then what I do is I just project the shortest distance to the plane and find that point. So this is my new object instead of going out. This doesn't happen when you are in discrete, like game settings, or when everything is discrete. This mainly happens when you are in continuous state space. So you need to do the projection. Okay, so I think I'll just write what. So policy gradient here. So there's actually policy gradient. So yeah. So basically is how you what is a performance measure, right? So performance measure. I think sir has defined. Okay. Do you remember for MAP the performance measure? Multi-amp magnets.
Yeah. Right. Epsilon pattern configured. Epsilon delta.
No. Oh no. Okay. Performance measure for reinforcement.
Okay.
1 by n. Some if you don't remember, it's fine. It's u n r i. This was for
Yeah.
those states.
Yes.
But now you need to bring into states. So you have basically pi s. So you need to bring this instead of pi a parameterized as theta, you have pi s comma a parameterized as theta. So in policy gradient, what you do is you don't do transitions, you take trajectories. Take the trajectory like okay, so truncate trajectory or whole trajectories, but finite number of trajectories. So truncate will come later. So first what you do is you have S0, A0, R0, S1, A1, R1, and put one. The subset implies what number trajectory it is. So I have set of this like trajectories. It is all the trajectories. And then my performance measure in this would be 1 by n summation equal to n to n. So I have n number of trajectories. Gi S0 S0 I call it. So drag Pi S0 I theta S0. So basically the reward changes to trajectory return, the whole trajectory return, such that you have started S0 S0 at the time. The probability of this thing, this is I is you're going over all trajectories. So this thing is probability given a theta, this is the probability that you see this trajectory. So now okay, grad Pi S0 I theta by S0 I theta. You can write as grad log Pi S0 I. I think this you would have better remembered. It is reinforced if I would have written it as log I, because log had that dou by dou theta of log, right?
Yeah.
So this term is basically dou by dou theta of log of probability.
Yes.
So this uses grad log. So now this I can write as grad log. So now suppose I fix so this is summation over all trajectories. Now suppose I just take one trajectory. Suppose it's the first trajectory P1 S0 theta. I'm just taking this. How do you write this probability?
I'm sorry, I didn't get you, sorry. Okay.
Given a theta, a policy pi is parameters with
Pi of that trajectory given theta.
okay, yeah. Instead of going whole trajectory, let's do it step like transition because you have MDP, because it's an MDP, because you have market.
Yeah.
So the first thing is first you have S0. So probability that it is at S0 into what your policy is defined by theta. Theta would give you a probable
action probability of action given
given
states.
state and
P of S1.
Yes. So okay, so this would be A1 S0, right?
Yeah.
This would be S1
S1 given
S0
S0.
and then pi of A2 given S1, or maybe this is 0. I have a A0. This is A0 A1 given S1. So I'll get a product like this. So
Yeah.
this I can write as grad of summation of log A0. So it will be A0 plus log pi A0 S0 plus log S1.
Right. Yes.
So now this gradient I'm doing on theta. As you see, all the transition probabilities, they don't depend on theta.
Yeah.
So they'll just not, the gradient is zero. No gradient. So the gradient will remain just over log. Now you have summation of logs, that becomes log of products. So that becomes log of pi a I si theta. This is equal to grad pi l si theta by pi I si. So basically what you have proved is this is equal to this. So you don't need to worry about the underlying transitions.
Right.
Just need to worry about
Okay, so we are essentially removing the transition probabilities from the MDT.
from yeah, no, there is transition properties in MPTEL,
But
but
we are not using it.
the way you're updating is you don't require them. Just require what policy. The policy has the information of what.
And if we have the transition probabilities,
You-
then it doesn't become a learning, but instead a planning problem.
Yeah, if you look like RL, the main problem is you don't have transition probabilities. That's why you don't want a equation which depends on transition probabilities.
Right.
So you have made your update rule, this update rule, which is similar to reinforce in MAB, but now we have modified it into something. So instead of taking each transition single, if you take trajectories, this nice splitting out of the transition probabilities and then gradient over zero would become zero. So all the transition probabilities would go away.
Yeah.
So that's why you sample it trajectories. In deep Q learning, in even Q learning also, you sample transitions.
Yes.
You have epsilon greedy, you sample your action epsilon greedy, and then you go ahead doing it. In policy gradient, you sample trajectories. Why you sample trajectories is because you want to update your policy, and you want to update your policy, and you don't want that update rule to depend on transition probabilities.
Yes.
So you sample on trajectories such that there is no dependency on the transition probabilities of the MPTEL.
Right.
So there is okay. So there is actually a now this is basically your update rule. Like your update rule becomes theta k plus 1 is equal to theta k plus alpha k into the gradient here is this term. So not this term. The gradient is average of returns that you have got in the trajectories that you have sampled. And the probability that, so this probability is now equal to this, so you'll get, so grad
Okay, one question I have is we start with the policy pi, right? Here also.
yeah theta the moment so here the policy pi is the moment I initialize theta, I start with the policy.
So instead of staying on policy, is off policy applicable here, like import sampling?
Off policy is applicable here. Off policy is applicable. You can do off policy.
So the same important sampling factors will come in,
Same
right?
important factor will come. But then you need to be careful while you're cancelling out those. Okay. Then it's okay. You can do it. You're right. So the important sampling actually comes in.
Okay. So how does the final gradient change with importance sampling?
There you get the gradient to be okay. There you have the important something you have y equal to 0 to infinity. phi theta at given st by phi ref at given st. The term inside the log. So it will log, yeah, something like this. Because now you have something with other something or something with this something. So now what was the question? Sorry. How would the gradient change, right?
Yeah. Sorry.
Which week was
Important something. I think it was week 5 or no, week 6. Oh, where is it?
not
Off
six.
policy. Off policy. Yeah, week 6. It's week 6.
Week 6.
Yeah. Off policy MC.
It's not sure. Even I can't see. I don't know why I can't see.
Right. So, the expectation comes around 1 by n summation over I f of xi p of xi by q of xi. That's where the behavioral policy and the other things. Estimation policy and behavior policy.
So P is
P is our estimation policy. Probability of trajectory given that I follow pi.
so basically you're averaging there your FIs would be the whole trajectory sums.
Yeah.
So the FXI would yeah. So these FXIs. These FXIs, let me write down here also. So this is what
FXI is given that it's the return on the trajectory. It's the return given that I take trajectory I.
Yeah, so expectation of fx. This you can write as 1 by n summation fx dx by qx, right?
Yeah.
So now it would change to your fx would be this GIS0, which is basically the return of the trajectory. And okay, so here you are not doing an estimation basically, expectation basically, but yeah, I think you can try to write this log, add log into an
Yeah, sure.
What the weights would be like?
Yeah.
Yeah, because this is an expectation with not this is not an expectation. Like this is an expectation, but we need to do some mathematical calculations there to change that into expectation. But you're right. This could be done in our policy also. This could be done in our policy. I just clarify what we do. Yeah, you are right. So this could be done off policy. Important sampling, okay, same important sampling what you said. Basically what happens is while running policy gradient, what you do is you truncate the you don't take it till infinity, you truncate it at some time t, and then you do the expected. There is actually a proof where to show that. Okay, what you show is. Where you define a random variable or obviously with summation equal to 0 to infinity grad log by maybe given st, and then you are maybe I'll write this with that left to you. And then your returns equal to e prime to infinity comma to what st prime. You define and then you return. So what this is actually, this is tail rewards. This is not truncate rewards, this is tail rewards. Tail rewards with the property of you getting a trajectory being there. You define a random variable system, then you say that expectation of this thing, right, is equal to expectation of f. So now expectation of f tilde, what you are trying to do is you are trying to find, so that is where your important sampling comes into play. So I hope you see it, but yeah, maybe the weights, they are not so straightforward to see.
I found out a link that gives the expectation. I'll post it here just for reference.
Okay. So off policy. So I'll add that link in my description. Does it give the weights?
No, it gives the expectations, not the final updates.
So actually, basically, policy gradient, you prove that expectations are same. The theory goes that you prove that expectations are same. Now, because you can't do expectation over all trajectories, practically what you do is you take trajectories, a finite number of trajectories, and then you take the sample. But to show that if you do off policy also, you will get the same expectation in some way. So summation p equal to 0 to infinity. So this is basically your GIST SI. So your trajectory, whatever the sample, this is your total reward that you're getting given a policy type and you're sampling from the trajectory. Given a trajectory, what is the total reward you're getting? Discounted reward. So basically your update grad update is basically this term. The expectation of f. This is your grad data.
Okay.
So this is actually equal to grad of your value function given a pi x times 20. It is not very straightforward, but I hope you see that there is a proof for this. I thought I would do the proof, but I will do the proof.
Yeah, maybe you can attach it as some additional resources.
Okay, I'll do one thing. I'll write it down in this notes.
Yeah.
And I'll post it on the Google Drive that way.
Sure.
So, and this gives you important sampling of policy weight. Because now okay, I think I'm using notations a bit also. Okay, I'll do one.
I'm sorry, you're dropping off.
Okay, so I'm misusing notations also here very much because f tilde, f and all many notations are newly introduced. But yeah, I'll write down the proof and I'll put it in.
Yeah, yeah.
Okay, so okay, so first, okay, let's go back to reinforce because all of this, okay, these are similarity between reinforce and policy gradient also, right?
Yeah.
So reinforce also had a reinforcement baseline type of updation for theta value at alpha t into rt
Yeah,
minus
minus B.
rho by rho theta of rt. This is for MAB.
Yeah.
There you had like if RT is greater than VT, it's a reduction. If RT is less than VT, it's a reduction.
Mm-hmm.
Those kind of things. So there VT was average of all was what you have received till now. So here VT becomes your average of all rewards starting from service. So what is the average reward starting from service?
Average removal trajectory.
Average reward, average, no, once you're given trajectory, there's no average reward. Let's go.
Okay, okay.
When you have average reward, it's the value of the state. So value of state starting from S. So
To some state T.
huh?
To some state T or infinity.
Infinity. Yeah. Maybe no, I didn't get the question.
No, the average reward starting from state S naught
S.
to T.
But I can let us be S.
Right, yeah.
And
Oh, expectation.
average expectation. Okay, expected reward. Average reward. Okay, yeah, my bad. Sorry.
No, it's just for me to correlate.
Okay. No, average reward is expected. Right?
Yeah.
Okay. Okay. Then G. This is one step below. RT is your what at time t what you are looking for. So this is GT of S. So this modifies.
Right.
This thing modifies to this. So this gives you RT plus PST plus 1 minus. Does this look like you have seen something?
TD.
Yeah, exactly. TD. This is TD. This TD error.
Yeah.
So basically, active critic does is it takes temporal difference method, it takes conjugate methods, it connects to another conjugate. That is active critic. So you have theta upgradation with something with value function upgradation. That is the basic concept. So this is your actor, which learns by policy gradient. This is your critic. Critic learns by error.
Okay.
So we have theta updates, we have the updates. Theta updates is basically alpha and this thing is your TDR, which I think this is alpha delta t into this.
Also, it's like basically I do policy iteration as well as value iteration.
Like you do only policy iteration, but your policy iteration leads you to keep a state of like you do policy iteration, your values in how
Yeah.
Yeah, I think I'm sure. You have any doubts? Like this is the basic concept of activity. Maybe I'll touch activity next time also.
Yeah, sure.
I'll jot down the proof and I'll. You guys have any other doubts? So you can go to Manas.
Aniket, one question. So, this out of two session, one is theoretical, other is practical kind of session, or what exactly?
Actually, we like both were asked to do whatever you're comfortable with. So I'm comfortable with theory. So it is you, but Pallab goes in more into practical stuff. Like he has more code stuff. I have more theoretical stuff. So if you're interested in theoretical stuff, you can enter in mine. But if you want me to do codes also, I'll do codes. That's not an issue. Panav is more comfortable with the codes.
Okay, I find that to be. Oh, yeah, thanks.
Yeah, sure, sure.
So I read this one interesting article with respect to behavior cloning.
Oh, okay.
Basically, you clone expert systems and then you train